So last we left off, we had our partial derivatives and we found our critical points. Now, the next thing that we need to do is decide whether or not those things or the behavior of the graph at those critical values is maximum or minimum. In the beginning of the week, we were just kind of doing this by inspection. We'd look at the plot, we'd see where that point was, and we would just say, okay, that's a maximum or minimum. But we can see that it's not as clear with certain surfaces. So we want to make way to the second derivative test here, which we said had to do with second partial derivatives. First, with respect to x, that expression times with respect to y minus derivative of x with respect to y. First derivative partial of x with respect to y. This is symmetric to the derivative of y with respect to x, so we end up with this term squared. And what that means is basically we just need to continue to differentiate. So we had our first derivative, first partial with respect to x as 3x squared minus 12y. So the next thing that we want to do is find the derivative of this with respect to x and the derivative of it with respect to y. So first, that would be fxx. If we take the derivative of this expression with respect to x, we get 3x squared, so that would be 6x. And there's no x here, so that just goes away. Derivative of that expression with respect to y, well, 3x squared goes away, negative 12y, we just get negative 12. Okay. Derivative of y with respect to y. Well, with our partials, we had the derivative of f with respect to y equal to 3y squared minus 12y. And if we take the derivative, or 12x, sorry. Take the derivative of that with respect to y, well, 3y squared, that's just going to be 6y. There is not a y in this, so it's gone. And here are the three second order partials that we need. And again, what we have is we have this symmetry. So why didn't we have to solve f of y with respect to x? Well, what is f of y with respect to x? There's no x in this term. It's just negative 12. And sure enough, that's the same thing as f of x with respect to y. It turns out that this will always be the case. All right, we can talk more about that if you'd like, but for now we'll just take it for granted and plug in, because we have to evaluate this expression for our critical points. So we have two critical points, right? First is when x was 0 and y was 0. And what I think the best way to keep track of this is to just make a little table. So we'll say, all right, at 0, 0, we had fxx, fyy, we've got fxy, and then we'll be able to figure out this value of the discriminant. So fxx, if we plug 0, 0 in, is 0. Yy is 0. Xy is negative 12. So if we substitute those values into our expression, we get 0 times 0 minus negative 12 squared, which is negative 144. And at 4, 4, we substitute in and we say, okay, xx, 24, yy, 24, xy, still going to be negative 12. And the discriminant, now we've got 24 times 24 minus 144. That's 596 minus 144. I don't know, 400 something. Doesn't really matter. All we're going to have to do is to compare this to 0, really. All right, and the last thing is to use these values to assess whether or not those points are maximums or minimums. But we had some criteria for that. So I'm just going to cruise back to our table here. We had these rules that said if the discriminant's positive and the second derivative of f of x with respect to x at that critical point was positive, then that was a minimum. So, we can just go through and check. So what was the value of our discriminant? Well, it was negative here. So if it was negative, well, then f has a saddle point there. And that's that. So at 0, 0, this must be a saddle point. Saddle. And if it's positive, which it is here, and then it's going to depend on the sign of the second derivative with respect to x. If that's positive, then it's a minimum. If it's negative, it's a maximum. And it's 24, so it's positive, so we've got a local min at 4, 4. And there we go. That's that. Now, there are ways to actually, this stuff happens so much that we have ways to organize and kind of make these operations more efficient. Namely, doing that multiplication that we just did to find the discriminant, we can organize our second derivatives in a matrix like this and then use matrix operations to actually find those products and evaluate them. Oftentimes we'll use a computer to do this. So next thing is to walk through just this same example using a computer. I ended up using SymPy because SymPy, it's easy to compute symbolic derivatives, Hessians, and determinants of functions. Now I need symbols, x and y. I need my function. And then I can evaluate the Hessian of this function, f of xy, with respect to the variables x and y. And sure enough, when I do this, I end up with 6x and 6y. Those were our partials, and negative 12 and negative 12. Those were our other partials. Okay? And to find that discriminant, what we actually do is we take what's called a determinant of this Hessian matrix. Now, we also need to evaluate that at each of our critical points. So to take the determinant is just this Hessian dot determinant. After the Hessian, I saved the results of this after having actually just displayed it here. So now I have this variable Hessian. I take the determinant of it, and then I substitute 4 in for x and 4 in for y, and I get my 432. Same idea, I can substitute 0 and 0 in, and I get negative 144. So that's what that number should have been, was 432. Similarly, I can find the symbolic derivatives of any order of that function. So finding the second derivative with respect to x, with respect to y, of x with respect to y, is as easy as this. Okay, I'm just finding the derivative of my function, specifying what variable I'm differentiating with respect to, and what order derivative I want. And this is just my determinant of the Hessian, the discriminant. And then I can organize this stuff in a table, and now I see the same kind of thing, right? Here's my critical point, fxx, fyy, xy, my discriminant. And then I can, if I want, I could even write a little function to apply some logic to this table to make those decisions, where I look at everything is dependent on fxx and this discriminant. So if fxx is positive and this thing is positive, it's a minimum. If fxx is negative and this is positive, it's a maximum. If this is negative, if the discriminant's negative, it's a saddle point, otherwise it's inconclusive. So we can just even work that logic into a function and apply it to tables of partial derivatives like this and get a label. So here we are. Got a local min and a saddle. Okay, doesn't matter if you understand any of this with a computer. I want you to just shake a couple of these out by hand this week. But you see that they're a little bit tedious, so take your time. There's only a couple, and enjoy.